Good morning. In this video, we will discuss floating point multiplication and floating point MIPS programming. So let's see the floating point multiplication. Let's assume that you have a scientific notation of a decimal number, like this is a decimal number 1.110 10 power 10. This is a decimal number, not a binary. See, this is base 10. Another number 9.200 10 power minus 5. So we want to multiply these two numbers. They are already given in the scientific notation. So now what we will do for multiplication is now consider the exponent. This is 10 power 10 and the next one is 10 power 5. So let's see the exponents. The first number has 10 and the next number minus 5. If you add them, you will get positive 5. So this is the exponent of the result. So let's keep this aside. Okay. And for the biased exponent, let's say if you want to do the biased exponent, very simple. The first number has the exponent 10 plus 127, you get 137 because we convert decimal into binary. For converting original exponent plus 127, you get a new number, that is the biased exponent for the first number. For the second number, which is 5 plus 1 minus 5 plus 127 minus 5. Here in the slide it's written positive 5, it's minus 5. Minus 5 plus 127, you get 122. Okay, so if you add these two, because we need to add the two exponents. So let me add the two biased exponent, I get 259. So the result is too large to represent in a 8-bit exponent field. So we'll have a mess here. Okay. So this is the problem with the biased exponent. If we add the like kind of basis. Okay. So this is the problem with the biased exponent because you can't represent 259 in an 8-bit as an 8-bit data. Let's see this one. So how to get the correct biased sum? When we add the biased numbers, we must subtract the bias from the sum. Okay. So 137 plus 122 minus 127. Here it is. 137, biased exponent of the first number. 122, biased exponent of the second number, minus the 127. So you get 132. Okay, so this is better. You can express this one as an 8-bit data. Okay, let's keep this exponent aside. Now let's see the Mantissa. Mantissa is the fraction part. 1.110 for the first number, 9.200 the second number. So you take the bit one by one. How do you do the multiplication? Normally, like the same way you do the multiplication. You know, in mathematics, how do you normally do the multiplication? When you do, you get this number. This is base 10. Okay. When you get this number, you know the original number has some decimal point. So, but in the result, you need to put the decimal point. So, let's see. The first number multiplicand, you have 3 decimal places. Even in the second number, you have 0.200, 3 decimal places. 3 plus 3, 6. So, you put the decimal point after 6th position from right to left. So, 0, 0, 0, 3 over 212. 3 plus 3, 6 digits over. So the result is 10.21200. Okay, this is the result, 10.21200. And this is about the fraction part. How about the exponent? 10 power what? See here you calculated the new exponent. 5 is the exponent for the result. So that is the 10 power 5. Here it is. Okay. So you can do in a normalized form. This is not a normalized form. 10.212 is not a normalized form. So move the decimal point to the left. You move to the left, you add a 1, the exponent. You see here. You move the decimal point to the left, you get 1.0212. The exponent becomes 10 power 6. So this is the idea. This is the way we can try to make the result as a normalized one. You see the result 1.0212. You can round the result. Keep 3 digits after the decimal point. So 1.021, because the last digit is 2. It can't. It won't be rounded up. Okay, so just ignore the last digit 2. The step is the sign. The sign of the product depends on the sign of the original operands. See, the original operands in the question, it is 1.110 and another one is 9.200. Both are positive. The sign of the result is positive. Okay, if both are the same, then it is positive. Like if both are negative, the result is positive. If the sign of the both operand are same, the result is positive. If the sign of the operand is different, the sign is negative. So just keep this point in mind. This is the algorithm for floating point multiplication. So the steps are explained in the pictorial form. This is another example, like you are multiplying two numbers 0.5, this is base 10, and then minus 0.4375, this is also base 10. Okay then, so in binary the task is the task is, so let's have the binary number, which is like 1.0000 2 power minus 1, and then minus 1.11 or minus 1.110 2 power minus 2, because this is the decimal number and the equivalent binary number is given in the next line. So this is the equivalent binary number. Okay, now we will do the multiplication in binary floating point. Okay, now let's see the exponent. 2 power minus 1, another one 2 power minus 2. Minus 1 minus 2, when you add you get minus 3. This is the result of exponent of the result. Answer, when you have the answer of the exponent of the result, minus 3. This one, next step explains the biased one. We can ignore for a while. Now let's see the multiplication. Your fraction. What is your fraction? 1.000. Another one 1.110. So just try to multiply as like a normal multiplication in mathematics. So you get this number 1110000. Now you need to put a binary point. In the original number, the multiplicand has 3 decimal binary places. After the binary point, you have 3 places, 3 digits. Even in the multiplier, the second number, it has 3 digits after the decimal point. You know the point, binary point. So 3 plus 3, it is 6. So put the binary point after 6 places from right to left, See, 0, 0, 0, 0, 4 over already, 1, 1. So here you put the point, like 1.11, 0, 0, 0, 0. And the exponent is 2 power minus 3. You just calculated the exponent for the result, keep the same, 2 power minus 3. It's already in normalized form. Don't have to normalize, only you round the result. Just keep 3 digits after the binary point. It will be 1.110 2 power minus 3. This is the one explained in detail. Now let's move on to the floating point architecture. Okay. Actually in MIPS, in MIPS we have 32 floating point registers starting from register F0 to register F31. So there are 32 floating point register in MIPS architecture. Each register can hold 32-bit data for the single precision. We studied in the previous part of this floating point. Single precision needs 32-bit. Double precision needs 64-bit. Okay then. So if you are going to represent double precision, so you just pair the registers 2, 2, 2. Now you have 32. You pair them, so you will have 16 pair. So you can represent 16 double precision numbers. So double precision numbers you can represent 16, which is you pair the register. F0 with F1, F2 with F3, and then F4 with 5, F6 with 7, sorry, F6 with 7, yeah, right, until the last pair. Okay. And we have we can do arithmetic operations on the floating point numbers even with single precision and even with double precision. So the instructions are very simple. Add dot s, subtract dot sub dot s, and mul dot s, div dot s. This is for single precision. Double precision you just add a dot d and then subtract dot d, something like that. Okay. Dot S for the single precision, dot D for the double precision. So you can have 4 arithmetic operations: add, subtract, multiply, divide. So we will see floating point transfer, floating point register transfer. Okay then. So we have move dot S, move dot D. These two instructions copy the data from one floating point register to another floating point register. Okay, register to register transfer, we have an instruction called move.s, move.d. Let's assume that you have a data in memory. Okay, you want to transfer the data to a register, or else you have like kind of you have some kind of uh, data in a normal general purpose register, which is a integer register. Okay, let's assume that you have data in integer register, which is T1, T2, S1, S2, S3, S4, something like that. You want to move to a floating point register, or you want to move from a floating point register, something like that. So here um, we have some instruction, which is move to C1, this coprocessor 1, move from coprocessor 1. Here C1, coprocessor 1 represents a floating point register. So what does it mean? Move to a floating point register. What does it mean? The value in the T register, general purpose register, the integer register, is moved to a floating point register. So what do you have the data here? Like for example, I have 25 here. 25 is moved to floating point. See the meaning? You see here, this is the meaning. Next one, move from coprocessor 1. Coprocessor means floating point register. So you have a data in a floating point register that will be moved to integer register, like a general purpose register. So what is the data? You have it in the floating point register that is moved to general purpose register. This is the meaning. We will see one example program for using this move to coprocessor 1, C1, move from coprocessor 1 when we discuss the conversion. Okay, not now because it is used with the conversion. So when we go to conversion, I'll explain these two instructions. Now let's move on to some more transfer. Okay, floating point register transfer. Okay, so here let's assume that you have a data in registers, and you want to move the data from memory to a register or from register to memory. Okay then, so here you are dealing with memory. So whenever you are transferring a data from register to memory or from memory to register, it is the load word and store word we already discussed with the integer values LW, SW. Okay. So the same thing we are going to use here, LWC1. Okay, C1 here represents the coprocessor 1, floating point. Okay, in SWC1 it represents what you have the data in a floating point register that is moved to the memory. That's the meaning. Store word, load word, the same meaning. But now you have a C1 here. That means you are dealing with F register, floating point register. So here it is mentioned C1 means coprocessor 1. Okay. We'll see one program on this. I will upload a program on this in the blackboard after a while. Now let's see some more transfer, floating point data transfer. So this is, we are going to move the data between the floating point register and RAM. RAM is memory. So you declare a variable in the program with a value. So that value is in the memory RAM location. That value you want to transfer to the floating point register, or else from the register you want to transfer to the memory. So you have L.S or L.D and some more called S.S store word. Store. S means store. Another S means single precision. Here S.D means store double precision. Okay. Let's see one example for this. Let's have a data directive. Here I declare a variable. Let's say this is A and the name is float. Sorry, the data type is float. The name of the RAM location is A. Let's assign a default value. Let's say 35.0. This is the value of the variable A. I'm trying to do some program with the like text directive. What I'm going to do is, I'm going to move this 35.0 to a floating point register and I'm going to print it. Okay. Moving to a floating point register. Load RAM to RAM value, memory value to a register, that is called L. So it is a single precision. Float means single precision. That means L.S, let's assume F2 and then A. What does it mean? This means it loads the value of A to register F2. This is the meaning. Now let me try to print the value. I can explain the printing. I'm printing a floating point value, which is single precision floating point. So this is called service number is 2 for printing single precision number, which is float. Okay, then move the data. You have a data in F2. When you want to print the data, you have to move it to F12. Remember. So move.s. Move.s moves the data from one floating point register to another floating point register. I want to move to F12 from F2. And then syscall. So this one will print the value. What value it will print? 35.0. I don't have anything. Let me make exit syscall. So let's say fp1.asm. What I'm doing, I'm having a value in a variable RAM location and I'm loading the value to a floating point register and printing. So this is the way how do you print. So let's see the compilation, no errors, and execution. See 35.0, it's now printed. This is about loading. Okay, let me do storing. Now your value of A is 35.0. Now I would like to change it to 55.0. Okay, so I'm going to have a like kind of so let me keep one more variable B. This time it's going to be a float again. So let's say 55.0. Now what I'm doing, I'm loading the value. I keep the same program. I'm loading the value of the variable A to F2 and I'm printing the value of F2. Now I want to change this value to 35 to 55. Okay. I want to take the B value. I want to put it onto the A value. Okay. So take the B value. Load.s F4. This time I'm using F4 and B. So I'm loading the value of B to F4. Now I'm going to change to A. Okay, this F4, I'm going to, what's the value of F4 now? F4 is, so register F4 is now 55.0. Okay, this is the value of F4. Alright. Now this value of F4, I want to move it to the memory location A. That means from register to memory, F4 to memory, that is store word. Let's say store word s.s. So let me put it onto A. What does it mean is store the content of register F4 to B. That's to A. So store the content of, save the content of the register F4 onto the location A. To the location, memory location A. This is the meaning. Okay then. So this is the idea of what I am doing. Do you get the idea? So what I am doing is I load the value of B onto a register. This is what you call load word. From register to memory, loading from memory to register is load word. And register to memory is a store word. Okay, let me write it here. Transfer data from memory to FP register. So what I am doing here in the second part is transfer data from FP register to memory. This is what I am doing. Okay then. So now what I am doing, let me print the value of B now. I'm going to cut it from here. Before when I print it, it was printing 45. Now I load the value and I change the value of A now. Do you get the idea? Now the value of A is not 35, it's now 55. So let me save it in another program. Okay, let's see the output. You see here now 55. Before it used to print 35. Now it is printing 55 because we changed the value of the memory location. It was 35 in the beginning. Now I change it. How do I change? Using the instruction called store s.s. If you are going to deal with a double value, it's very simple. Let me save it in a different program. This is a single precision. Now I'm going to do a double precision. Very simple. So you just say the storage type is float. From float to double. And then here it's no more as load.d, store.d. Very simple. You don't have to do anything. Even here load.d, even here move.d. One more change is this one. 2 means printing single precision number. Now I'm dealing with the double value. So 3. So this means double. 3 means double. Remember, for printing, 2 means printing a syscall service. 2 means printing a single precision. 3 means printing a double precision. Just keep this point in mind when you are doing the program, dealing with the float or double or whatever. One more thing. If you declare okay, let me come to the point afterwards. Let's see the output. You won't see any difference. It's 55. Okay, here it is. It's 55. Even before also it's 55. Is it? Because the number is small, so you won't see that much difference. Okay. One more thing. In case if you declare it as a float, A is a float. I'm storing the value. I'm using s.d, something like that. A is what? A is a float value, but the instruction I'm using it s.d. When I try to do this type of program, just a second. Okay, let's see. This is a double value. Let me keep it a double. Let's say 1 second. And here you are doing with maybe a single. Okay, it's a double value, but you are dealing with a single precision number. So let's try to see, because it's a small number, so it still works. But the output, what you see, 0.0. Actually, it's not 0. You go to the program, you still have a data, is it? But it's not showing the output, correct output, because it's a double value, but the instruction you are using is a single precision instruction. You get the idea? So you have to maintain the uniformity. If you are dealing with a single precision number, use the single precision instructions. When you are dealing with a floating point number, a double precision number, use the floating point instructions. Let's go back to the slides. This is about the load word and store word explained. This is what you do with a base, like a based indexing. Do you remember in load word and store word, we have based in displacement indexing, direct load word, indirect, something like that. In arrays, we use this. This is what we do with the floating point array. When you create an array and you have an array of floating point numbers, and there are an array of 5 numbers, and you are going to load one by one onto a register, and you want to do something. So here you will be using this way. You can use the load.s like this. It's something like the load word, what we normally do with array. Normally in integer array we say LW, SW, same thing. But I'm using a floating point register here, but this is the base address. Base address, normal register. Can you see here in the slide they say register 4. It's an integer register. Because base register, it's not going to be a floating point. Do not use a floating point register for the base. Okay. So we'll see one example for the arrays. So let's see one example for array. What I'm going to do here is I'm going to initialize and floating point, single floating point or a single precision. Array of 3 numbers. This is my question. You are going to array of floating point numbers. It's not an integer array, floating point array. Initialize an array. It's going to have 3 elements. I'm going to print only. There is nothing, no calculations. Even you can do calculation. You know how to do addition, subtraction, everything you know. Okay, let's see the array. Very simple. Let's declare an array. Let's say A. This is the array name. What is the this is single precision floating point number, so float. If you want a double, we can have double. So see the question asks single means go with the single. So A is the array name, float is the storage type. Initialize, let me initialize. Let's say 1.1 is the first number, comma 0.2, comma 3.3. There are 3 numbers here. Okay, any number you can write even without the like 3, it's okay, fine. I didn't give point whatever, it's okay, no problem. Automatically it will be 3.0. Even though you don't write 0.0, because it's a float, automatically 0.0 will be added. Okay, now let's see. The question says initialize and print. So we initialized already. I want to print the values. Printing means you need a loop, because we don't know how many values are there in the array. So I need a loop for the array. Okay, it's a normal loop. You studied a loop before in one of the exercises. Even with the integer array, you used loop. It's a normal loop. No new changes. I need a counter. Starting counter, ending counter. So let me use register T1 for the starting counter. And register T2 for the ending counter. How many? And the loop will start from 1, 2, 3. So this is the ending counter. Now I want the base address. So LA, maybe let me use T0, base address of the array. Base address of array A in register T0. So the loop is going to start from 1 to 3. This is the meaning. Starting counter, ending counter. How do you write a loop? Let me write a loop. Later I will fill the loop. You say branch greater than, and then starting counter, and then ending counter, and then you say exit. And here you say jump loop because it has to go second iteration, third iteration. After jump exit, you have the exit. I don't have anything, so you will be terminating the execution with syscall. Okay, fine. So this is your loop. How does a loop looks like? Inside the loop, what I'm going to do, I'm going to print the array number. Printing the array number. Just printing. You know how to print a float number. In the previous exercise, we saw how to print the float number. The syscall service for the printing is 2. Floating single precision is 2. And then what you want to print, you have to put it in register F12. Where is my value? It is in array. Array means it is in memory. I have to load it to F12. So, of course, it is load.s. So, how do I load in F12? You just now studied the same way, offset with the base address. The same way we can do. Offset is 0 always. Base address, it is in T0. Just to keep the base address in T0 and then syscall for printing. That's it. It looks like your normal printing for the integer array. Only the difference is you have L.S and then you have the floating point register. There is no change. Here it is 2. Before you used to say 1 for integer. Alright. Don't change this one. This is a normal register. T1, T2, T3. Because they are all going to keep the integer value. 1, 3, base address, they are all integer value. They are not a floating point number. There is no change here. Okay, there is no change in the loop. There is no change in the jumping, in whatever. Only the change here is services 2 for printing single precision. The load is now different. It's load.s. Okay, and then floating point register. Fine. Now you print already. Now I want to increment the counter, increment the base address. Very simple. Same like what do you do? Counter is T1. You increment by 1. And then the base address. So that is T0. So let's say T0, 4. That's it. This increment also there is no change. Okay, fine. So let me save this one. And let's see the error. There is no error. And the output. When I see the output, can you see it goes like 1.1, 2.2, 3.0. Can you see the 3.0? I initialized 3 only. But it is 3.0. I told you. Even though you give a whole number, 0.0 will be added. But the output is not clear. It's all coming in one line. I want it in line by line. You know how to do it. You just keep a message, maybe B, and then ASCII Z, and then you can have a \n. Then that one you can print it after here. This one. Printing a message. You know how to print a message. Register V0, 4. LA register A0, B, and then syscall. After printing the number, print \n. So now, output may look different. You see previously it was on the same line. Now it is like 1 by 1. 1.1 and then 2.2 and then 3.0. Something like that. Okay. So this is the way we deal with the arrays in the floating point. In the same way we can do with the arrays. You want to calculate the sum of the numbers of the array. You want to do whatever you want to do. So you can do all those things. Like you want to check the array elements. That one we will see after a while. Okay. Like you want to add the sum of elements. We can do that. Just a second. Now let's see this here. I created a new program You are going to initialize an array of 3 single precision floating point numbers. Now let's see double precision. Okay, and then we are going to print the sum of the 3 elements. So those 3 elements I'm going to sum. I'm going to print the sum only, not the values. It is a double precision. So it's a double. So let me keep the same number 1.1, 2.2, 3. It's 3.0, whatever is it. Okay then. So here, I'm going to use a loop because it's an array. Array may have many elements. I don't know how many elements in the array. I initialize, I know. But in case, if you are going to read and you don't know how many elements will be there, so better to have a loop, is it? Of course. So I need a starting counter, ending counter and the base address. Now let's start the loop. This is the loop. You start the loop like this and you have increment for the base address and starting counter. You have the jump loop, you have the exit, whatever. Okay. So inside the loop, what I'm going to do, calculate the sum of the array elements. That's it. Okay. I'm calculating the sum of the array elements. Let me put the final answer, sum of the array elements. Let me use F12 because I'm going to print. So why not I keep the answer in the F12 itself, or else maybe another F2 maybe. Okay. So so what I'm going to do, let me keep it in F2 or F12 or whatever. Okay. And then let's see, addition. I'm going to add the value. First you need to load the value, then only you can add the value. So load.d, D means double precision. This is a double precision number. F2 and then base address is register T0. Offset is 0 always. Okay. So you load the first number. Where is it? It is in register F2. Okay. Now I add it with the sum. So add dot D maybe F4. Register F4, comma, the one I loaded F2. This is the meaning. This is in Java, we normally do like sum equals sum plus a of I, something like that. We do like this. Do you remember in Java? When you study the array, you do like this. Sum is equal to sum plus a of I. So, destination is sum. Even the one of the source is the sum. See, can you see here? This is the sum. One of the source is also sum. This F2 is the array value, a of I. Because you load it onto the F2. Am I right? And then you increment the array count, starting counter and then base address and go back and do it continuously. And then you print the answer. So when you come to the exit, print the answer. So let's see, printing the double precision answer. So the service is 3 and then now it is move.d. Okay, fine. You put the value in F12. Where is the result? F4 contains the result. This is call. That's it. Don't do any printing inside the loop. Inside the loop, you just load the value, calculate the sum. Outside the loop, you print the sum. That's it. So here I print the sum. Okay, fine. So let's see how does it work. No errors, but it has a double. Okay, there is something called line number 5. There is a warning in line number 5. Or can you see here? This is the warning. Spelling mistake. Okay. Remember, when you have messages with the array declaration, you need to keep the array declaration first. Do the array declaration and then write your messages. You should not swap the order. Like messages come first, array declaration comes later. No. It will give you error message. So there is no errors. Let's see the output. There is an exception in line number 14. Okay, so there was a runtime error because the runtime error is because of the double precision. When you see double precision, it takes 64, sorry, it takes 64 bits for one double number. Double what? Floating point number. So one floating point number needs a 64 bit. Okay. So if you are incrementing by 4, it will be going every word like 32 bit. It jumps to every 32 bit. Okay, so 4 means it will jump to the 32 bit. But I have to jump every 64 bit. So you need to double the increment. So every 2 register, not 1 register, every 2 register you have to jump. Can you get the idea? So that's the idea. So here remember whenever you are dealing with a double array, increment is by 8 because each element need 2 words. 2 word means 64 bits. So the address has to be incremented by 8 because 8 into 4, 8 into 8, 64 bit. Okay then. Before we had 4 into 8 is 32 bit. Now 8 into 8, 64 bits. So that's the idea. So now let's see the sum of the three numbers. 6.3. The first number is 1.1, 2.2, 3. So it's 6.3 and it's a double precision. So that's what it's coming like this. Okay then, long precision. Okay, let's go back to the slides. So this is about the arrays. So I show you two example, one with single precision and one with the double precision. Okay, and this is about LI instruction. LI means what? Load immediate. Immediately you want to load a value to a floating point register. We have an instruction called li.s and li.d, but this instruction is not will not function in MIPS architecture. So we will ignore this part. Okay. Now let's move on to conditional jumping. You want to compare a floating point value with another floating point value. Like you have a value in register F2, another register F4 contains another value. You want to know, are these same value, or is it this one contains big number, that one contains big number? You want to compare. So we have a conditional branching instruction. You call it conditional jump. Okay, let's see that one first. In floating point, we have to do this checking in 2 steps. First, you have to compare the values in the floating point register. Then you need to set a code in a special register. Set a code means if the condition is true, you set the code to 1. 1 means true, 0 means false. Okay, so first you have to compare, then you have to branch. So there are 2 instructions. Remember, for conditional jumping, it's not like integer, like branch greater than, branch less than. No, it's not like that. In floating point, first we have to compare. Then we have to branch. Separate instruction. What are the comparisons available? C dot equal dot S. C means compare. Compare for equality. Dot S means single precision. Compare for less than, equal. You see LE. Less than or equal. S means a single precision. And this one LT. LT means less than. Only less than. So this is for single precision. If you want to do for double precision, write dot D everywhere. Okay then. Now branching. After you compare, meaning is written here. See, let's see the first example. C dot equal dot S. F2 comma F4. We are comparing. Is it the value F2 is equal to F4? If it is true, the code will be set to 1. If it is false, code will be set to 0. 0 means false. 1 means. Then you need to have the branch. You have 2 options. You want to have branch true, branch coprocessor 1 true, branch coprocessor 1 false. You can have anything. False means you are checking the false value. Is it code value is equal to 0? Then you do something. Or else, if you are going to do branch C1T, then that means you are checking. Is it the code value 1? 1 means true. Then you go to somewhere, jump to a label. See, label. Okay, that is the meaning of conditional jump. Let's see one example. Let me have a question like read two single precision numbers, floating point numbers. After reading, check for or compare or check or whatever, check for equality. This is the question. I'm going to read two single precision number and I'm going to compare them. Are they equal or not? So I may say they are equal. If not, I will say they are not equal. That's it. So let me have a data directive. So let's say message 1 for input. Enter two single precision FP numbers. So let me put a backslash n so it will go to the next line. The number I will type it in the next line. That is the meaning. So another message. They are equal. I will say the two numbers are equal. Okay, just a message. No need to print the numbers. So if you have equal, then you need to have for the double. So now we will see how to read a floating point value, single precision number. This is called service for reading a float number. Single precision number is 6. So register LIV 0, 6. Okay. So service number for reading single is 6. For double it is 7. That's it. Okay. Then you have the syscall. After syscall you need to move somewhere. Is it? So where to move? Let me put it in F2. Automatically the number you type, it's always automatically saved in register F0. So you move that value to register F2. See, when you are executing this program, okay, so when you execute this program, you will be typing a number. Is it? Automatically the number goes to F0. Don't keep the number in F0, move it to another floating point register. This is what I'm doing. I need to read two numbers. So the first number is 2, F2 means I have the second number F4. Here I forgot to write the message. It's better to have a message for the input so that the output will be clear. So message 1 and then syscall. So that enter two single precision number will come, and this is for reading a single precision number. If you are planning to read a double number, you put a 7 here and then this is move.d. That's the only difference. So now I read 2. Now I'm going to compare. What you need to do? You have to compare first. So compare register F2 and register F4. Okay, so how to do? Compare dot equality. This is a single precision, so let's write yes. If not, write D. Okay. So first register is F2. You can change the order. It's not a problem. So I'm comparing two. No need to write any label. If the F2 value is equal to F4 value, the code will be set to 1, or else code will be set to 0. That is the meaning. Now I'm going to branch based on the value. See, branch coprocessor 1 true. Even though for single or double, no matter, maybe you are dealing with the double precision also, single precision, it is branch C1T only or F. Is it F or it's up to you. Do you want to use T or F? What is the meaning is you are branching the value is true. Branching if the value is false. That is the meaning. Okay, so let me use true. Go to if the code value is, what if the code value is 1, if the condition above what you check, if the condition is true, I go to equal. That is the meaning. Okay. If the condition is true, T means true. If the condition is true, I branch to equal. That is the meaning. Okay, let me write it. If the result of the Comparison, what you do on the top. A comparison is true. Go to label. Label what? Label equal. This is the meaning. If the comparison result is true, branch to label equal. Go to means branch. Branch to label equal. That is the meaning. So you need to have a label called equal. And then what do you want to print? You want to print the message equal. 0, 4, A0, message 2, I guess, and then syscall. After this, I don't have anything, so let me have exit liv0, 10, and then syscall. Let's assume that if the comparison result is true, I go to equal. If not, I go to the next line. What I print not equal. After you print not equal, there is nothing to do, so jump exit. See, you see what I am doing? I am comparing the two registers for equality. If they are equal, code will be set to 1. If they are not equal, code will be set to 0. I am checking. Is it true? The above condition, is it true? Go to label equal. And in the label, I print message equal. If the condition is not true, if the result of the condition is not true, it comes to the next line and this message will be printed and jump exit. This is the meaning. Let's see the output. This is called spelling mistake, double L. Okay, no error. Enter 2. Can you see here? It is printing a message for the input and now it is blinking. Enter 2 single precision number. Can I say 5.5 and then another number 6.6? They are not equal. The two numbers are not equal. Let me run one more time. Let me give like 5.5, another number also 5.5. Same. So the two numbers are equal. You see this one? So in the same way, you can use the less than equal or less than only. LT, LE. LE means less than or equal. LT means less than. So there are three. Either you use equal, you use less than equal or less than only. But if you want to check for greater than, it's very simple. Okay, let's see one more program. Don't have a greater than option. Let me go to the slide. We have equal. You are comparing for equality, comparing for less than or equal, comparing for less than. Only these three options are there. You do not have option for checking greater than. How do I do checking for greater than? Let's see one example. So here check for, or I copy the same program. Print the greater number. Which number is big? I am going to print that number. Okay. I don't need these messages like the greater number is the big number. I mean something like that. Okay. So reading is same. It's a single precision. I don't have anything to say. Can we see for double precision now? As we saw single precision for the first time. Let's see double precision. So it means 7 here. This is called service for reading double is 7. Here also 7. Here double. And one more change is move dot D. It's not move dot S, it's move dot D. So let's see how do you read double precision number. Very simple. Syscall service is 7, move dot D. That's it. And now you are comparing. So you are comparing this and this for greater than. I don't have greater than, by the way. Okay. So use the other way around. Okay. What is the other way around? For greater than, the opposite is less than or equal. Okay. You see, for greater than, opposite is less than or equal. For greater than or equal, you need to use the opposite one, which is less than only. Okay. I'm going to use less than or equal. Okay, why I am using less than or equal? Why not less than? See, if I check with less than, fine, no problem. But if I don't check for equality, even though if like I give two number 5 and 5, it will still say greater number is 5. Do you get my point? So I don't want the less number, I don't want the equal number. I want only the greater number. So whatever you don't want, keep it here. Don't want a less number, I don't want a equal number. I want a greater number. See? So that's what I keep it here. So I compare, is it F2 less than or equal to F4? I'll go with the, okay, let me say label 1, not label, whatever is it. So let's see what is the meaning of this is, if the result of the comparison is true. Okay, this is a double precision, so D, don't forget it. I'm checking, is it F2 less than or equal to F4? Then I go to label here. In the label, what is the meaning in the label is, this is the label. In the label, F2 less than, which is greater? F4. Printing the F4. F4 is a what? F4 is the double precision number. This is called service for double is T for printing double number. Okay then, remember this point. So move dot D, where to move it? In F12. What is the answer? F4. See, I'm comparing. Is it this F2 less than or equal to F4? What does it mean? F2 is less or F2 is equal to F4. Okay, can you get the idea? F2 is equal to F4. Okay, this is a problem. Less only. Okay, no equal. Equal, I can't say this is equal or that is, because anyway I have to print the number. The question says print the number. So you are checking only for greater than. Sorry, so mean to say greater than means it's less than. Okay, so no equal please. I'll tell you how to do the equal in a minute. So I'm checking for less than. Is F2 less than F4? What does it mean? F4 is the big number. So print F4. In case if the condition is false, what does it mean? F2 is the big number. Can you get the idea? If the condition is true, F2 is small, F4 is big. I go to the label, 2 means I go to the label, the big one I print it. If the condition is false, I mean the F2 is the big number. Let's see. I still have to check the equal. Let's do it after a while. Okay, no errors. So enter 2, actually it's a double precision, but anyway, I change the message. Okay, let's see 5.6 and the another number is 6.5. So the big one is 6.5. It's printing 6.5. I forgot to print the message. So let's see the message. Okay, now you will have the message. Enter 2 number like 456 point something and another number is 345 dot something. So the greater is 456. Alright, let's do one more time. Like 123.45, another one is 909 point something. 909 is the bigger. Okay, fine. One more time. Let's see 5.5. Another number is 5.5. So it says I give the two numbers same. 5.5 and 5.5. It still says the greater number is 5.5. No, it should not be. There's no greater. They are all equal, is it? So let's have a message. Both numbers are equal. Before you continue to proceed, after you read the two numbers, before you do the printing the message and comparing the two numbers in between, you try to check for equality. So compare equal, it's a double value. First number is F2, second number is F4, sorry. And then if branch coprocessor 1, true means you go to equal. Okay, equal. If the two numbers are not equal, you print this one, you compare the less than whatever is it. Fine. So now you try to have the equal, print a message saying that message two numbers are equal. This is message 3. Okay, let's see how does it work. Two numbers, let's say 5.5, another also 5.5. So it says both numbers are equal. The same program I modify a little, like for example 5.6 and 6.5, still says which is bigger. 6.5 is the bigger. Okay, so let's go back to the slides. This is about the conditional jumping. So in floating point, how do you do? First you compare the floating point numbers and then you branch. Okay, so two, it comes together. Branch and so comparing and branching comes together. You choose which one you have to. Are you checking for equality or not equality? Are you checking for less than or greater than? Or less than or equal or greater than or whatever. It depends on which condition you want to branch, for true condition or false condition. You can use any of them. These are some of the instruction set for the floating point. We already discussed some for addition, like same way for multiplication, division and subtraction for the float and the double. And the branch comparison also we discussed, comparison and branching. For load word coprocessor 1, I explained L dot S and S dot S, L dot D and S dot D. That is, you can use it instead of LWC1, SWC1. Explained the L dot S, L dot D. Store word for single precision, store load word for single precision, and L dot D, S dot D, same function. Okay. Now we move on to the floating point functions. What do you mean by floating point functions is procedures for the floating point. Okay then. So you can have procedures for the floating point value. So we already studied procedures. If you have if you are going to write a procedure, if you want to pass values, you keep the values in register F12, 13, 14, 15. If your procedure is going to return a value, you will be using F0 and F1. Okay. And if you want to use some caller saved or call is saved, use these registers, the remaining registers. Okay, whatever registers you don't have, use the remaining registers. Okay, even the same registers. Okay, why not? You can still use them. So these are some basic ideas before you start your procedures. So floating point functions, that is for floating point procedures. So you will have the registers F12 to 15 for the passing value and F0 and F1 for the return value. Fine. So let's see one example using functions means procedure. So let's do a procedure that deals with the floating point value. That means I'm going to pass a floating point number and the procedure is going to return a floating point number. Something like that. Let's see one simple example. Okay, this is the question. So you are going to read a single precision number and you are going to pass it to a procedure and calculate the square of the number, print the result in the caller. Caller means main program, not inside the procedure. Inside the procedure, you are just calculating the square. That's it. Okay. So let me straight go with the text directive reading. Single precision. So syscall service 6. And then move.s. I will do one thing. I'll read a number and I'll pass it to the procedure. In the slide, passing means you place them in F12, 13, 14, 15. There are 4 registers F12, 13, 14. So let me put it in F14. Automatically when you read, the number is in F0. So I am moving into F14. That means I am passing the value. Okay. Now I call the procedure. Jump and link procedure. Same like before. You know previously how do you call? The same way. So I go to the procedure. What I am doing, inside the procedure, calculate the square. What does it mean square? Multiply by itself. So mul.s, see, I calculate the square and I have to return it so that the answer will be printed in the caller. So returning means, let's go to the program. I have to use F0 or F1. Okay. So let me use F0. So I'm returning the value. Okay. So multiply by itself. Where is your number? F14 has the number. Register F14. So sorry. Multiply by itself, register F14, register F14. So in this way, I calculate and I return the value. Nothing to do now. So jump register RA, same like before. So in the caller, so this is your caller and this is your procedure. From the label until the JR is your procedure. Inside the procedure, you calculate the square and return the value. In the main program, you read a number, pass it to the procedure and print the result. So here, jump register means it goes to the next line after jump and link, which is line 10. It goes to line 10. So now you print the result. It's a float number, so it is 2. Move.s, F12 and then F0 and then syscall. After this, I don't have anything. You have to write the syscall service for exit. Let's assume that you miss the syscall service, the execution will end up in infinite loop. So do not miss the syscall service for the exit inside the program for the procedure. It's compulsory, or else you will end up in what do you call infinite execution. So let's see the output. It is asking, it's blinking. Can you see down here? I don't have a message. So that's what it's straight come here. So let's say that 7.5. Okay, it's maybe easy number. 5.0. So double. Multiply by itself, 25. See, 25.0. Multiply by itself. So this is the way you can use floating point number in procedure. Only thing you need to remember is everything is there. Calling the procedure is same. Returning back to the caller is same. And you know, only thing you need to remember is where to pass the parameters and where to return the values. This is the new change. Normally the called caller saved and callee saved, use all of them. So it's not a problem. Only thing you need to remember these two things. Okay, how to pass a parameter to the procedure, how to return a value to the caller. This is for a floating point constant. How can you initialize a value? This one I already explained in one of the example. Data directive, create a variable, and this is the storage type of float, and you initialize a value. Alright. And then how to move it to a register, load.s. So li.s, it's not working. That's one I told you, ignore this one. Okay, the last one. This is example code. You can go through it later. Now let's move on to type conversion. What do you mean by type conversion? For example, you have a floating point number that is of double precision. I want to convert to a single precision, or else leave it. Maybe you have a single precision, I want to convert to a double precision, or else an integer to a double, or integer to a single to integer, or a double to integer. You know, you can convert from any type to any type. Okay, this is the idea. Single to double or double to single, or integer to a double or integer to a single. Okay, or double to the integer or double to single. Whatever conversion you can do it. So this is the opcode CVT convert. This is the opcode. You have to write like this. CVT dot. You write two things. S means single. D means double. What is this W? W means integer. Okay, so remember. CVT dot S dot W. This means you have an integer number and you convert to a single precision. This is the meaning. Type convert from. So this is from. And the one you write yes is the convert to. I want to convert from an integer, convert to a single. This is the meaning of this opcode. CVT.S.W. And the parameter. What you need to write? You need to write a two floating point number. You can't write a T1, T2, T3, no. S1, S2, S3, no, nothing. Both of them has to be a floating point number. Always the first one is the destination, second one is the source. You have the source value in F2, the result will be stored in F4. That's the meaning of this. There is a simple example given here. This is a word to single word. See, word means we use register T0, T1, S0, S1, something like that. So, you see this line LI T0 32. What does it mean? I have a value 32 in register T0. Now I want to convert that value 32 to a single precision number. What I do first, because in the convert statement, can you see above? Convert SW, S.W, fine. I have to write two floating point register. I should not write T0 here. So move the T0 to a floating point register. So this is the instruction. Move to coprocessor 1. How to write? First write the normal general purpose register, comma, floating point register. So this T0 value is now moved to F2. Now you call the convert statement. So the F2 value is converted into F2 contains what? 32. So 32 is now changed to single precision, float number. That is 32.0. That's the meaning. This move to coprocessor 1. Okay. Move to coprocessor 1. Okay. Let's see one example. So let's see one simple example like convert an integer to a single precision number. Okay, so let me go straight to the text directive. Like I keep the value T0 is for example 456. Now I have to convert. Convert means what? CVT dot. First you have to write what you want to convert to. The result. Result should be single. And from what? From word. So a word means W means word means integer. So the integer is converted to single. This is the meaning. Now the result I will put it in register maybe F12. Okay. And the source I will take it from F2. Register F2. But my value is in T0. I should not write T0 here. Now can you see the instruction? CVT S.W. You have to write a float register, comma, another float. You can't write a T0. No, this is not possible. Error. Okay. So let me write F2. So I have to put this value 456 in F2. Okay. How to put? Move to coprocessor 1. This is a single precision. I write coprocessor 1. If I'm going to convert to double, write dot D. Something like that. Okay. So now move to coprocessor 1. First you need, can you see the syntax? First you write the general purpose and then the floating point register. So general register, your T0 moves to F2. That's it. What do you have it in T0? That is moved to F2. And F2 is converted to a single precision number. Let's print F2. Li register V0, comma, single precision. So And then you already moved. F12 contains the result. So I don't have to move it. You already moved to F12. So just to say syscall. Okay, can you get my point? I already moved the result to F12. So you don't have to write a statement to move F12, F12. It's already been moved. So just write the 2 steps. Enough. So let's see. No errors. And then when you execute, it was I assigned 456. Now it is printing 0.0 because it's already been converted to single precision number. This is about like kind of converting from integer to single. If you want to do integer to double, very simple. You put a dot D here. Okay, here if I say double, let's see, it's a double precision. Wait a second, it's a dot D, and you convert to D, and then it's now going to be 3 for printing a double precision. Okay, let me save it in another number, maybe another program. It's the same thing, but I'm now dealing with the double precision number. So it's still going to be the same, but I'm using a simple number, 456. Double precision can deal with the big number. Okay, it's a lot big number. Okay, anyway, this is fine. Okay, then this is about from integer to single or integer to double. Can you see the other way around? Single to integer. Okay, let's copy the same so that it's easy for me. So now I want to convert from single or double precision number to an integer. Okay, let's see this. So I don't have to initialize anything. Of course, I need a double precision number. So let me declare it in data directive a double number, which is maybe something like that, whatever number. Now in text directive, let me load it L.D. Back to port, maybe F2 contains the number A. Okay then. So I have a double number which is 345.67. So I load that value in F12. So F2, sorry, it is F2. F2 contains this number. Okay, fine. Now I want to convert this double number to an integer. Okay. So to an integer. Okay. So I want to convert a double. So from, write it in the second part. In the first part, what do you want to convert? I want to convert as an integer. Do you get my point? So this is from a double, I convert to integer. Okay, so the F2 is 345.67 and it will be converted into only the whole number, not the fractional part. It will be truncated. Okay, so this contains F12. I want to print the value. I want to print the integer. Now it is an integer, is it? So we say move register A0, comma. Where is the result? You put the result in F12. I can't do this. I have to write a E register or S register. Is it? So let's say T0. So what is T0? You have to have one more instruction. Your original number is in F2. It is 345.67. You convert as integer. You keep the integer in F register. No, you have to move it to a normal register. So move from coprocessor 1 dot D. Okay. So I want to move it to T0 from F12. This is the meaning. So the result is in F12. Move it to T0 into T0. That is the meaning. Let's see, I have to save it in something. No errors. And then see 345. Originally it was 345.67. Now I convert to integer. So the point something is removed already, truncated already. So what is the value of T0? T0 is only the 345. I print the value of T0. What I am doing here, just go through one more time. This is convert. From double, I convert to integer. Integer means word. Okay, so your double value is in F12. Your word means integer is in your double value is in F2. Integer is in F12. But integer in F12, F is a floating point register. Why are you keeping the integer in a floating point register? Move it to a general register. Okay, so I'm moving from coprocessor 1. Coprocessor means floating point. Okay, so move from coprocessor dot D, because this is a double value. You move from F12 to a normal general purpose register. Now I print the value of T0. Okay, fine. Let's go back to the slide. Reading and printing. While explaining the program, I explained how to read a single and double values, how to print a single and double values. This is an example for reading and printing. And this is the floating point programming. Thank you.